So imagine with me for just 1 second. You're a math student and you're trying to figure out the area of a function under a curve between 2 points. Let's say A and B. I like that. What are you going to use? Are you going to use the left sum equation? Are you going to use the right sum equation? Or are you going to use the Riemann sum equation? It seems a lot of choices, and they all seem a little bit complicated. A lot of squares, a lot of sums, just overall a mess. But let's say I have a solution for you, and that solution is the fundamental theorem of calculus. My name is Lane Sanders, and although I'm not a mathematic professional, believe me, I'm far from it, I believe I can teach you the fundamental theorem of calculus and why it's relevant to the real world. So, we got to start off, like always, with a little bit of history. With a little bit of magic thrown in, of course. The magic, of course, that being math. What on earth is the fundamental theorem of calculus? Well, it was formed and proved by James Gregory in the 1600s. He basically described it as the relationship between derivatives and integration, and it is a way for us to define definite integrals without using Riemann sums, basically making everybody's lives just that much easier. This was improved upon by Isaac Barrow, giving his own improved form, which slightly changed a little from the original. And then it was improved on even more by Gottfried Leibniz, who took this further and, in fact, coined the phrase the fundamental theorem of calculus. After this, about a century passed, and then this was taken even further by that one rock star scientist we all know and love. No, not that guy, even though, yeah, Brunel was a cool scientific rock star. Yeah, that guy. Before he was knighted, the not yet Sir Isaac Newton was developing his laws of motion, along with his laws of gravity, and just all his laws. In his third law of motion, he states that you can solve velocity and acceleration by using the fundamental theorem of calculus. You can use it to find the first derivative, which gives you velocity, and the second derivative, which gives you acceleration. So, what if I told you there were two parts of this? Yeah, there are two parts. The first part, which is basically this whole thing right here, states that the function of f, if it's a real valued and continuous function, of course, and let's say it's on an open interval, I like I. Let's go with I. And any number in I, if f is defined by the following function, then you get all of this. Basically, this states that the function f takes the value from a to x, and you evaluate it with the function f of t and the derivative dt, and you'll get all that. This also states that the derivative of x is equal to this function f of x here. So that was part one. Oh, crazy, right? Well, wait, it gets even crazier. Well, or simpler, depends on how you look at it. With the second part, it's similar, but there are a few key differences. The second part states that if f is real valued and is continuous, but this time is on a closed interval, well, a and b, what goes around comes around, and let's say f is the indefinite integral of f on that integral, then we get this function here, which states that on this integral a to b, the function of which is the function of f of x dx, this will give us the function of f, the big F, with the value of b minus the function big F with the value of a thrown into it. In other words, we take the antiderivative of f of x, the small f of x, and then we plug the values of b and a into it, and we take what we plug the value of b into and subtract it from the value of a we get, which gives us something along the lines of an area. So, why is this so important? Why would we want it? What on earth could we gain from it? Well, as one of my greatest math teachers told me back in 11th grade, he described the fundamental theorem as the total of all the little changes in one big thing. You can find a lot with the fundamental theorem of calculus. You can find net change over an area of time. You can find the total area of a shape. You can find the average value of a function over a region. You can find a lot of things. And you could take this a lot into real life. You could, let's say, find the total decrease of a liquid in a tank using this. Especially when you throw 3D shapes into the mix. Oh Lord, you're going to have fun then. You seem a little skeptical? Well, that's good, because I'm about to show you some real-life examples with my magic camera changer like this.
Alright, thanks to that little bit of magic, we're back with this example. So this example is pretty simple. This is the function of x is equal to the interval of 1 from 1 to 4 of the function x squared minus 1 dx. So what we're going to want to do, we'll go ahead and write f of x here. And then we're going to do something that just for this one, we're going to split these up. We're going to do from 1 to 4, x squared minus the interval of 1 to 4, 1 dx. And we're going to put dx here too. So then we're going to go ahead and take the antiderivative. So the antiderivative of x squared is x cubed over 3. We're going to go ahead and draw the line 1 to 4. This part is always important. That shows that you're ready to plug in these numbers into this here. Next, we're going to do the antiderivative of 1, which, if you know your antiderivatives, is just x. I'm going to go ahead and do that too. So we're going to do this. We're going to go ahead and plug in these numbers. 4 minus, that will give us 64 over 3 minus 1/3 minus 4 minus 1. That'll give us 3 here. And then here's the kicker. So that'll give us 63/3, which gives us 21. And 21 minus 3 is equal to 18. All right, so that's a simple one, right? A little bit of work required, but nothing too major. Oh boy, just wait for this one. The next one, example 2, is the f of x is equal to the interval of -2 to 4 of 4x squared over 3 minus 32x, sorry about that, plus 55 dx. So what we're going to want to do, we're going to split these up again. This time we're going to do a little bit different. We're going to take 4/3 out, and we're going to do -2 over 4 x squared. Then we're going to do -32x, -2, 4. Then we're going to do plus that. We're going to do -2 to 4 again, but with 55. So we'll go ahead, we'll work backwards. We'll do 55x here. That's from -2 to 4. Here we got 32x squared over 3 from -2 to 4. And then over here we have x cubed over 3. We multiply that back. We got 4/3 here, and then we have that from -2 to 4. After all that, get down here, get 32 minus, so 32, 32x, that's what we do a little bit of that. That is 192. And then this kicker, -2 and then 4. So we're going to do half, so just multiply it by, that's 330. And adding all that up, doing all that, that'll give us 170, and that is our answer. So that is a complicated one. We are able to use the fundamental theorem of calculus to solve that. But did you know that you can also solve, pi related problems? Well, I have one last example here. And this one is the function f of x on the interval of -pi to 2 pi over 3 of cosine dx. That doesn't seem too terribly complicated unless you used to have a fear of pi's like I did. Let's go ahead and do this. So the antiderivative of cosine is sine, obviously. And then over here we have -pi, and then we have 2 pi over 3. So we'll go ahead and split these off. We have sine of 2 pi over 3 and minus, and then we have sine of -pi. Sine of -pi is 0, so whatever we get here hopefully will be the answer. and you run through the whatever you run yours through, you run it through the pi circle, which I did for this. This will be root 3 over 2. We subtract that from 0. Our answer here will be root 3 over 2. And that is our answer, root 3 over 2. And that shows that we can use this also shows the versatility of the fundamental theorem of calculus. This shows that not only can we use this for whole numbers as we did these last two examples, but this also means that we can also use it for pi-related problems. And that opens us up to things like circles, anything that uses pi in problems, we can also use the fundamental theorem of calculus for. So we'll go back to the slides with a little bit more of magic.
Alright, now that we're back on these slides again, let's go over what we've learned today. We've discussed what the fundamental theorem of calculus is, who discovered it, who improved upon it, and who took it to its limits, why it's so important to our society today, and how to use it, and how to apply it to our mathematical equations. Well, I hope to see you again soon. Oh, and here are all the sources that I used. Thank you very much, and goodbye. Alright, now that we're back on these slides again, let's go over what we've learned today. We've discussed what the fundamental theorem of calculus is, who discovered it, who improved upon it, and who took it to its limits, why it's so important to our society today, and how to use it, and how to apply it to our mathematical equations. Well, I hope to see you again soon. Oh, and here are all the sources that I used. Thank you very much, and goodbye. Alright, now that we're back on these slides again, let's go over what we've learned today. We've discussed what the fundamental theorem of calculus is, who discovered it, who improved upon it, and who took it to its limits, why it's so important to our society today, and how to use it, and how to apply it to our mathematical equations. Well, I hope to see you again soon. Oh, and here are all the sources that I used. Thank you very much, and goodbye. Alright, now that we're back on these slides again, let's go over what we've learned today. We've discussed what the fundamental theorem of calculus is, who discovered it, who improved upon it, and who took it to its limits, why it's so important to our society today, and how to use it, and how to apply it to our mathematical equations. Well, I hope to see you again soon. Oh, and here are all the sources that I used. Thank you very much, and goodbye.